Hi everybody. I'd like to introduce some key words on inclined plane scenario. For example, a scenario like this. An object with mass m slides down a frictionless plane inclined at angle theta. What is its net force and what is its acceleration? I want to look at how the key words in this problem indicate some values to us. I also want to note that I only gave as variables here m and theta. I'm also going to use g for acceleration due to gravity on Earth, but these could be real numbers in a real class problem. Let's take a look at how we'd approach a problem like this. And the first key word I really want us to notice here is that this plane is frictionless. That's going to be very important here. Let's dive into our problem, but keep in mind that our plane is frictionless. So, let's set up all the forces that are acting on this object. And of course we have our gravitational force, that is directly downwards. We have our normal force, which is completely perpendicular to the surface. We do not have a friction force, so I'm not going to draw that here. And we have in fact drawn every single force that is acting on this object. Our gravitational force downwards and our normal force outwards. Our next step will be to break one of these into its components. And remember, on these problems, you want to think of your planes as parallel and perpendicular. So which value do we have to break up into x and y components, or parallel and perpendicular components? The gravitational force. On inclined plane problems, you break your gravitational force into its components. So we break it up into its components, and you always remember that this angle here is equal to the original angle from the horizontal. So this would be theta right here. Theta 1, theta 2, those are the same. So we could find our parallel and perpendicular components. Our parallel component, if you notice that this goes across the plane, if I drew it up there, is going to be equal to mg times the sine of theta. And our perpendicular component is equal to mg times the cosine of theta. If you're wondering where those are coming from, you should rewatch the last video, or notice that sine is opposite the angle and cosine is adjacent to the angle. Now we found our two components of gravitational force. Our question here was, well, what is the net force on this problem? Let's take a look at what forces are balanced here. And if you look on our perpendicular plane, all forces are balanced on the perpendicular plane. We have this perpendicular force downwards and in, and this normal force outwards and up. And those have the same value. So this normal force you could also say is mg cosine theta. So our net force in the perpendicular plane is 0 newtons. What about in the parallel plane? Let's take a look on the parallel plane here. What is our net force on the parallel plane? Well, we have this parallel component pulling down the surface. Do we have anything pulling up the surface? The answer is no, we don't, because it is frictionless. So what does frictionless mean for us? It means that the net force on the parallel axis equals mg sine theta. And because the perpendicular axis has no net force, this is the net force of the entire system. So our net force in a situation like this is equal to our force parallel, which is mg sine of theta. If you see the word frictionless on a problem like this is always true. On a frictionless surface, net force equals the force parallel, which is mg sine of theta, where m is the mass of the object, g is the acceleration due to gravity on Earth in this case, and theta is the incline angle. That's on a frictionless surface. Let's add to that. The next question is, well, what is its acceleration? How can I find acceleration if I know my net force? Well, I know net force is equal to mass times acceleration. So we would simply divide by mass. Let's take a look what happens here when we divide by mass. Well, our acceleration is going to be mg sine of theta divided by mass. So what is our acceleration on a system like this? It is g times the sine of theta. It is the parallel component of the acceleration down the surface. So again, frictionless, we know that net force is mg sine of theta, and acceleration is g sine of theta. All of that implied simply from the word frictionless plane. These are always true on a frictionless plane. Let's add to this and show, and of course you could sub in real numbers here and these would work out just fine. Let's add to this and show a similar scenario, but where it's no longer going to be a frictionless plane. And I'm going to give you another key word here that I want us to really notice. And the other key word here that I want us to notice here on a new problem is, well, an object with mass m slides down an inclined plane at angle theta with a constant velocity. And I want to go into, well, what does this mean for us if it has a constant velocity as it slides down the plane? In this type of question, you might say something like, well, what is the net force on this object? Or you might say, well, what is the force of friction acting on this object? So let's look at this scenario. And we draw out our diagram, and once again, we have our angle theta, 90-degree angle down here. We have our mass of m, and we draw out the forces acting on this object. What forces are acting on this object? How many? Well, we have a gravitational force directly downwards towards the center of Earth, equal to mg. We have a normal force perpendicular to the surface. And now, it does not say frictionless. In fact, it says constant velocity. So we're also going to introduce our force of friction here, which is parallel to the surface. In this situation, it says it has a constant velocity. Well, let's take a look. We break this into its components, as always, and we get that the F perpendicular is going to be mg cosine of theta, because this angle here is also theta. We have the F parallel is mg sine of theta, and that's going to be pulling down the surface, that mg sine of theta, pulling down the surface. Well, in a situation like this, let's start with what's its F net. You actually knew that before even starting the problem. What is the net force on an object that moves at a constant velocity? The answer is the net force here is 0 newtons, because the acceleration is 0, and net force is equal to mass times acceleration. So we know right away our net force is 0. Well, let's take a look at the balance in these objects. If the full net force is 0, that means the net force on the perpendicular axis is 0 newtons, and the net force on the parallel axis is 0 newtons. Let's analyze both of these axes. On the perpendicular axis, what does this tell us? It tells us that the normal force is equal and opposite to mg cosine theta, this perpendicular component pushing in. But we already knew that. This is in fact always true on these problems, unless there's like some angled force acting on it, which we're not going to deal with in this class. But the parallel is a bit more interesting. On the parallel force here, what you'd want to notice is, well, our force of friction is up, our mg sine of theta is down. Those two forces must be balanced. So in a situation like this, we could say, well, net force parallel is equal to the force of friction plus the mg sine of theta, aka the force parallel, down the gravitational force parallel, mg sine of theta. And what does that mean for us? Well, our force of friction is equal and opposite to mg sine of theta. So what is the magnitude of its force of friction? It would be mg sine of theta. If you have a constant velocity, then force of friction equals mg sine of theta. Something worth writing down. If you have a constant velocity, force of friction is mg sine of theta. Mass times gravity times the sine of the angle. Again, always going to be true when they say a phrase like constant velocity. The last situation I want to bring up here, and this is actually only going to apply to AP physics. This is not something that is on the Regent. But I am going to just include it in this video for everybody anyway. Let's take a look if we have a situation like this. And let's say we're going to add one more situation here where we have this object. This has a mass. And I'm going to say there's an applied force pulling up the inclined plane. So let's say we have an applied force pulling up the inclined plane. We still have our angle of theta, we have our gravitational force downwards, we have our normal force out, and we have our two angles here separating this. So this is going to be our force perpendicular, which is mg cosine of theta, and our parallel, which is mg sine of theta. And what I want to say here is when applied force pulls up the surface, when applied force is pulling up the surface, what direction is our friction force? What direction is our friction force? And the answer is our friction force in that case will be down the surface, because friction force is always opposite the direction of motion. So in a case like this where you pull up like this, the friction force changes direction. Here the friction force pulls down the surface and is added to our force parallel, whereas our force applied is upwards and opposite. In a case like this, let's say we have an applied force pulling up the surface. If we have an applied force accelerating upwards, well, we have a new set of conditions here. In this case, how do we calculate our F net for the whole system? You would say, well, you have a positive applied force up minus our force of friction down minus mg sine of theta, which is our parallel component of gravity. This is an equation that'll work in this case where an applied force is accelerating up. Notice that the direction of motion switches the direction of friction, because friction is always opposite the direction of motion. Those are some key words on inclined planes, such as frictionless, constant velocity, and applied force accelerating upwards, and we'll take it from there.